Hey, so in this video, we're going to learn and see how to convert entire polar curves over to their Cartesian representations, or vice versa, converting a Cartesian equation over into a polar curve. So whenever we're doing any of these types of converting from polar to Cartesian, vice versa, or translating them back and forth, we're going to call on those equations that we derived that gave us relationships between those polar coordinates and Cartesian coordinates. And now we derive these equations based off of what we knew about right triangles and seeing the relationship between Cartesian or rectangular coordinates and these polar coordinates r and theta. And in this video, instead of going and converting single individual points over to one coordinate system to another, we're going to convert entire curves. So for example, let's consider this case of converting a curve in a Cartesian form over into the polar curve form. And the equation we'll consider first is 4y squared equals x. So the name of the game here is anywhere there's an x and a y, we want to try and replace those with things only in polar coordinates. So all the x's and y's we want to get rid of, and we only want to see r's and thetas back. And what's a little non-obvious here is, even though we want to go between Cartesian and polar, we have to think about this in a slightly different way than when we converted just individual points from one coordinate system to another. So I'm actually going to get rid of some of these headings that we had before when we use these for converting individual points. And the reason for that is, what we want to do in this bottom example here is basically anywhere there's a y, we want to get rid of that y and only have r's and thetas. Anywhere there's an x, we want to get rid of that x and only have r's and thetas. And it turns out that the equations that will actually help us the most, for example, are the ones sort of on the box on the right-hand side. And the reason for that is we know exactly what x is in terms of r and theta, and we know exactly what y is in terms of r and theta. So we're actually going to be able to take that information and directly substitute it into that curve. So anywhere there's an x, we can replace that with r cosine theta. And anywhere there's a y, we can replace that with r sine theta. And now we just have to be careful because that y is squared. So I'm just going to put a r sine theta squared there just so we don't forget about that power. So the next step, I'm just going to rewrite that previous line. So anywhere there's a y, we had r sine theta before. Anywhere there's an x, we have r cosine theta. And well, at this stage, we've gotten rid of all the x's and y's. We have fully some relationship between r's and thetas only. But we can do a little better than this because we can actually solve for r equals something. So we know what the polar radius is equal to as a function of the angle theta. So let's try and find the explicit form for r equals something. So on this left-hand side, we get 4r squared sine squared theta. The right-hand side, we just still have r cosine theta. And we just want to go ahead and try and solve for r. So divide both sides by an r. So we can get rid of one factor of r on the left. And then we're going to divide both sides by 4 sine squared. So we get r is equal to 1/4 cosine times a 1 over sine squared theta. And actually, we could do a little bit better than this if we want to write this in maybe some other trig forms, but I'm just going to say this form would be sufficient because we've gotten rid of all the x's and y's, and we have an equation that says r equals something. So I'm actually going to group one of those signs under that cosine, times a 1 over sine. And the only reason I'm going to do this is basically just so we're seeing a practice and remembering some of our old trig friends. So on the right-hand side now, we have r is equal to 1/4. We can write that as a cotangent of theta times a cosecant of theta. So in this example, again, we started off with this Cartesian equation, and we're ending up with its polar curve representation. R is equal to some function of theta. And again, this was possible by using those translation equations. Well, let's do another example, except this time take a polar curve and convert it into a Cartesian equation. So this time we have r is equal to 6 cosine theta. And again, the name of the game here is we want to convert, instead of x's and y's into r's and thetas, we want to convert all of those polar coordinates r and thetas into Cartesian x's and y's. So we're going to go back to our conversion equations. So I'm just going to recall those really quickly. Again, I'll get rid of some of those headers that might be slightly misleading here. And we just have to see what will help. Well, in this case, again, we want to go from r's and thetas into x's and y's. So we basically have to just start substituting things. So for example, the first thing I might try and do is get rid of this cosine. And why is that? Well, at least if I get rid of this cosine of theta, I'm not going to introduce any more thetas. So I'm inching closer towards maybe only x's and y's. And in fact, if we look at what cosine is equal to, we can see that cosine of theta is equal to x over y, or sorry, x over r. So we can write that r is equal to 6 times x over r. Well, you might be wondering, hey, we introduced another r at this point. Aren't we trying to just go x's and y's? Well, what's nice about these types of going from polar to Cartesian, we always know what r is equal to in terms of x's and y's, just based off the relationship from that Pythagorean identity. R squared is equal to x squared plus y squared. So we can always convert an r into x's and y's rather easily. Well, next up, let's just do a little bit of algebra. And in fact, let's multiply that r over to the left side. So we get r squared is equal to 6 times x. And now we can see, well, it might be time to get rid of that r squared. And we can actually go above top and see that r squared is equal to x squared plus y squared. So let's make that substitution. So we have x squared plus y squared now is equal to that 6x. And at this junction, we're actually able to get rid of all those r's and thetas, and we have a full equation only in terms of Cartesian coordinates x and y. And what I'm about to do is just go a little step further, because we can actually show, maybe in a slightly familiar form, what this equation actually represents. And I think this will just be a little bit of extra practice for us. So the spoiler here is I'm going to show that this is a circle. And right now, this equation sort of looks like a circle because that x squared plus y squared on the left, but this 6x term sitting there on the right-hand side, because we have a 6 times a variable, in this case x, that's not what we like to see on the right-hand side, so of a circle-like thing. So this isn't exactly an equation of a circle in its familiar form to us. So let's do a little bit of algebra here. So the first thing I'm going to do is I'm just going to subtract that 6x from both sides. So on the left-hand side now I have an x squared minus 6x, and then I have that plus y squared. And on the right-hand side, well, we have a 0. You might be wondering, why did we do that? Well, if we're remembering our equations of a circle, we like to see circles sort of like x minus some number, quantity squared, plus maybe y minus some number, quantity squared, equals the radius squared on the right-hand side. And right now, well, the right-hand side looks like a 0. We're going to see that that's going to change in a moment, but we're sort of inching closer to this form of x minus some quantity or plus some quantity squared, y plus or minus some quantity squared as well. So let's see what this actually looks like. So we can really convert that y into y minus 0 squared, just to show that it's closer to our general equation of a circle that we talked about. And well, we need to do a little bit of mathematical massaging on the x term. And the way in which we actually try to go about and do this is say, what I really want to do here is complete the square. And what that entails is basically adding or subtracting a number to both sides so we can actually reduce that fact to x plus or minus some number quantity squared. And in this case, we have this minus 6x. So what we do is actually take that, divide that by 2, and square it. So in this case, what we actually want to do is add to both sides a plus 9. So that 0 on the right-hand side will actually become a plus 9. Because remember, what we do to one side of the equation, we can do the other side, or we need to do the other side. So that left-hand side now becomes an x minus 3 quantity squared. We have a plus y minus 0 quantity squared. And we can actually rewrite that 9 as well a 3 squared. And this is a more familiar equation of a circle actually for us in this case. We can actually see this is sort of in the more familiar circle form where we have x plus or minus a number plus y plus or minus a number, both of those things squared individually equals a radius squared. So in this case, what we actually have is a circle with a radius equal to 3, and it's centered at 3, 0. Either way, this little bit of extra algebra completing the square, really showing its more familiar kind of circle form and all of that, that was a little bit just extra to practice some algebraic stuff that we may not have done in a while. The central focus of this last example really was this first part. We're starting off with a polar curve in r and theta, and we want to get rid of all those r's and thetas and turn them into x's and y's. So we just use a couple different equations from our polar Cartesian kind of translation path to finally get that into some curve where there's only x's and y's and no more r's and thetas.